Hello everyone, thank you for joining me on this talk, and let me start it with a short story. A few years ago, I was a gliding pilot and the contributor to the open source tactical flight computer. My software was used by many different pilots all over the world, the best competition pilots on the competitions, and also by casual pilots doing their regular flights during the weekends. It is when I realized how important is my software, how important it is to write the safe code in order to make sure that people depending on your software for safety are basically safe in the air. And don't be worried, you are on a good talk here. This is not a physical units talk, but this is when I started to write the library, physical units library, which turned out to be heavily relying on C++ templates and metaprogramming tricks. And I was also amazed how new techniques and introduction of C++20 features helped me in this task. So today we'll talk about my experience with this travel, with this journey through designing and implementing the library, and also through standardization of the language and the readiness of the compilers while we're providing, for example, concept support. My name is Mateusz Pusz. I'm a principal software engineer at EPAM Systems, and also the contributor and member of the ICC++ committee and MISRA C++. Today we'll be talking about metaprogramming, about rethinking the approach to this practice, to this coding practices and patterns that affect the user experience. So we'll start with the user experience. We'll talk about how user perceives our code when, for example, it doesn't compile, or when he starts or she starts to debug it. We'll talk about new toys in the toolbox. So what's new in this domain from C++20, for example? And also, we'll talk about things that can be provided soon to us. So about future proposals and possible changes to the language. And we'll finish the talk with performance. So because C++ is about providing the performance, right? We are doing this because this is the fastest language in the world. Otherwise, we'll be doing other languages like Java, C# or Python. But we care about the performance, so also I have to talk about performance a bit here. But we'll not talk about runtime performance because in this case, it's as fast as possible, but we'll be talking a bit about compile time performance because this is what bothers many of us heavily or the most. But first, let's scope on the user experience. As I said, this is not a physical units talk, but still I will be providing some samples from this domain. And that's why I have to introduce some concepts to you for you to be aware how such a library works. This basically is really similar to what we have in stud chrono duration. So we can, for example, divide the quantity of length by a scalar and get another quantity of length, right? We can convert units. So we can compare, for example, hour with seconds. We can add kilometers and meters and compare them to meters. This is already what we know from chrono, right? So that's nothing new. However, physical units library doesn't care about only one dimension. It cares about more. So you can find here, for example, conversions between two different dimensions, between kilometers and seconds. If you divide those, you will end up with speed. If you multiply speed by time, you will get length. If you divide length by speed, you will take time. Also, it's not about operations on different quantities because you can operate on the same quantities, and from multiplication or division of those, you will also get different quantities as a result. So for example, if you multiply length by length, you will get area, right? If you divide length by length, you will just get a scalar, something that's dimensionless. And if you will divide dimensionless quantity or dimensionless value by quantity of time, you will get a frequency. And this is where template metaprogramming starts here for my case. And this is where I learned all of the tricks that will be presented here. Let's start with a simple example. Let's try to implement a average speed function that takes length and time and returns speed. And that's a really simple calculation, right? Average speed is just a distance divided by the duration. So I want to use this function with different units. I want it to be unit. Basically, it has to be generic. It has to take any unit, any system of units, and basically return the speed in the same system of units. So if you provide speed in kilometers, I expect the results in kilometers per hour. If you provide speed in miles, I expect the result in miles per hour, right? So it has to be unit agnostic. Of course, it has to provide compile time safety. We want to make sure that if some calculations are not right in our program, that the program will just not compile and will fail to compile, will provide error log, and it would be good to provide nice error log so user exactly knows what's the issue there. I want to support multiple units, dimension, prefixes, like SI prefixes that are magnitudes of 10 or data prefixes that are magnitudes of 2. And of course, we don't want to have any runtime overhead. So there should be no intermediate conversions, for example, to dimension or quantity base units and back. And the program basically should perform as fast as the user would write it on fundamental types like double, or even faster, because it's possible actually with strong types. As an example of user experience, let's scope first on Boost.Units, which is the most popular library on the market doing this. To implement our average speed function, we are creating quantity of length and quantity of time and providing them to those function. And then you are returning here the quantity of velocity. So we are dividing those. And as you can see, this is really nice and easy to maintain a program, right? Everything is clear, everything is visible. We see the types here. It's easy to maintain. It is thanks to template aliases that are being used everywhere here and in many different libraries all over the world. So those template aliases improve developers' experience a lot. But what about the user experience? Let's make an error here. This error with a star here makes this calculation not correct. The quantity returned from this calculation is not a speed, right? Not a velocity in this case. So what the user sees? User will see something like this. This is a long error line saying that something is wrong. And this is generated by GCC. And if you will be careful enough, you will see that this log ends with 3 dots at the end, because this is not the end of it. The end of it is here. And by the way, I didn't mention, this is only the first line of the error log with the type that basically produced the error. And it's followed by many other lines with the, let's say, stack trace of the template instantiations. So this is only the first line that's so big. But this is GCC, right? The GCC tends to provide long error messages. GCC probably Clang is better, right? Because Clang is always claimed to provide better user experience in terms of error logs. So let's see what Clang does. This is the first line of the error log with Clang. It is shorter, right? It is really, really short. But actually, does it help you? Do you know what's the error here? You see some 1, -1, a lot of dots, and that's all. There's no information what was the error, and actually you don't have any information provided here by the compiler to know the context. So maybe GCC was better because it provided all of the context there. So I claim that sometimes shorter error messages are not necessarily better in this case, right? Let's see also another library. So to not just talk about Boost.Units, let's talk about maybe NHolthaus units, which is a really nice library and has a lot of users and is really nicely designed. And I chose this library for those slides because it provides it shows totally different solutions to do the same thing. And I will show you what's the result of that. Basically, developer's experience is again really nice. You have meters, seconds, meters per second as a result. It looks nice, but again, this is thanks to template aliases or just aliases. If you do the same error in the calculation here, you will see such a short error log. Static assertion, units are not compatible. Some type trait failed to execute. It looks nice, right? However, you know what's the cause of the error, that units are not compatible, but you know what are the units here? Maybe yes, because it's a short function, you know that's a meter, that's a second. But imagine that this is a function template, that you don't know exactly what's the unit here. Or maybe that this function has like 10 or 20 lines of calculations with intermediate results on the way. So basically you don't know what's the type provided to this calculation, to this type trait. And that's a problem, right? So static asserts are also not the best solution in many cases for good user experience. And also are not the golden bullet for everything, because you cannot static assert things and make overload resolution work fine, right? They don't affect overload resolution. This is quality of implementation rather than the interface of the function. So we can only provide quality of interface tricks here rather than change the program flow or whatever. And for some compilers, actually, as you see here in the case of GCC, doesn't provide context to know what's the source of the problem. You just know what is the problem, but don't know the source. Clang here actually is better because Clang provides the instantiation of the type trait that failed. So you know the context, right? But do you know what's the error? Again, you see a huge template instantiation here, rather than an alias, for example, with a lot of commas, a lot of 1, 1, 1, 0, 1, 1, 0, 1, and you don't know what's the error. And this is again caused by the aliases that are used by the developer to have a good developer's experience. But during compile time error logs, you see the type. The type aliases are lost really quickly during the compilation process. So I claim that we need to modernize our toolbox. Maybe in most of the template metaprogramming libraries, compile time errors are rare, right? It's really hard to make string or vector fail to compile. You have to do something really, really stupid in order to make it not compile and provide you a huge error log. But there are some libraries, with physical units library being one of them, that are different. Actually, in case of physical units library, the whole purpose to create this library is to create many of those error logs during a day for an engineer working with units. So if you're an engineer working with physical units library, you will be depending on this library to generate errors, and you want those errors to be easy to understand, rather than huge error logs that you have to analyze half an hour to know what was the reason of the problem you provided in your calculations. So in the case of this library, I had to rethink the way we do template metaprogramming, and I will show you some tricks and some solutions that basically address our talk's title today. But user's experience is not only about compile time error logs, like we've seen on the previous slides. We also affect here the debugging experience. For example, let's analyze the same function, the simple function with Boost.Units here, And let's make a breakpoint in it. This time we don't have any error. It compiled fine, but we want to put a breakpoint inside this function. The IDE I'm using here was totally lost with these types. See here, this is Boost.Units quantity of Boost.Units unit double. This is D, and T is Boost.Units quantity of Boost.Unit unit double, which basically looks like the same type. But they are not the same type, right? As you can see here, definitely these are different types, but IDE was lost because the template instantiation is so huge. So, but yes, maybe it's not it's a specific IDE, but I can always go to GDB and use command line, right? So this is how the breakpoint looks in the command line. Again, you have a huge template instantiation, and you don't know exactly what were the types provided to this function. You can see that the user experience in debugger is totally different than the developer's experience that is using aliases in the code, right? This is much easier to read than this breakpoint information. If you type ptype on specific variable here, you will get a type of it. To learn what it is, or any other variable in the application, but it's still a huge type, even bigger right now, because also the defaults of the template are provided in this list. So I claim that type aliases are great for developers, but not for end users. And developers cannot live without them. Yes, you cannot probably imagine writing code without template aliases. You don't want to type basic string all the time with all of those template instantiations there, right? You just want to print things like stud string during type stuff like this during the code, and have stud string rather than stud basic string of car, chart traits, and allocator and whatever there, right? So they simplify our developers' experience, but they are lost during compilation process, and then error logs are much longer. So the end user gets huge error messages. And it's a pity that we still do not have strong type devs in the language. Walter Brown, that provided keynote during this conference on the first day, was trying to standardize strong type devs for many years, provided many proposals to the committee, but none of them succeeded. And until now, we don't have them in the language. We have to use aliases or other techniques to improve this experience. Most of us use aliases, but you've seen what's the result of it. It's not the best for the end users. So what we can do in some cases, doesn't work in all cases, but in my cases it works correctly, is you can use an inheritance. You can inherit from some long template instantiation and provide a type for it. So for example, imagine that you say that this is a stud string and this is basic string with all of this instantiation here. Of course, string is different case here, because string has probably one of the biggest interface in the standard library. It probably has more than 200 overloads. So it's not a good solution here, maybe, because of all of those constructors, operators that will not be properly inherited from the base class. And also, it's questionable if we should inherit in a non-polymorphic way from an, let's say, smart class, smart type. But in this case, those are only tag types without any implementation, without any any functions, actually, not only special members. So they are empty inside and no members as a data. So in these cases, we can just assign strong types to their instantiations. Similarly to strong type devs, they do not vanish during compilation process. Member and non-member functions of such base class, basically taking this base class will also work with the child class, because this is how inheritance works, right? You can always provide derived class to the interface requiring the base class, and it works. But what's different to the strong type devs is they do not inherit the constructors as assignment operators. You can, enforce the inheritance of the constructors with C++11 statements, but still it doesn't work that nice as you could imagine. So it takes a bit of twittering if you have easy, non-trivial class to work with. So it doesn't work for everyone, but for some things like tag types, it's a perfect solution. However, I had a problem to solve here. We have a simple stuff here, right? We have a speed as a result, and we are dividing length by time. So we have quantity of dimension length and quantity of dimension time. We are providing this to the division operator inside the quantity class. So we have two different dimensions here, and we get a result. The result, calculated by the library, will be the result saying basically this will be some dimension that has length in the numerator and time in the denominator, right? Because it's exponent 1 and minus 1 here. And that's all. It doesn't know that's a speed by the framework itself, because speed is something assigned by the user with inheritance here, right? The framework is not aware of it. So how to make the framework aware of it? So the framework can substitute always this long class template instantiation with a nicely friendly user name provided by the user with the inheritance. So this is where downcasting facility started. First version of it basically was a simple type trait, saying downcast traits by default is type identity. So basically, if you provide some type T, you'll get a type T as a result. However, if there is a specialization of it, so you can specialize it for some class, for example, our dimension speed here, you can say that if you will see such a long instantiation like derived dimension of exponent dim length in exponent 1 and time to minus 1, then say this is a dimension speed as a result of this conversion, of this substitution of types. So with this, if you provide those instantiations, then those instantiations, those specializations, then basically you get the downcasting, right? Because this is source type, this is the resulting type, and basically this will work correctly. But the problem was that I had to put this everywhere in my code. Imagine that you have a SI system, for example, to implement, and there are hundreds of different dimensions and units, and you have to put this template specialization in every type provided. It was really inconvenient. And that's when I actually attended CppOnSea last year. I sat with Richard Smith by one table, and I asked him if we can find a better solution for it. And he provided one. Actually, I was really amazed about the language and how it works, because it seemed that I didn't understand everything. And basically how it works. This is our inheritance, right? We have this long type and a nicely user-provided types. For the slideware needs here, let's assume that we have alias for this long type. So basically this inheritance looks like this one, right? We have this long dimension instantiation and nicely provided name by the user. And how the downcasting facility works right now? It is basically injects two classes, two CRTP, so curiously recurring template parameter pattern idioms here, that basically provides the base for the downcasting, and it takes this type as a parameter. That's why I said this is CRTP. And also the child class here that's provided between the child class and inherited class here, with also provided first parameter as CRTP here, and the second is the target of our downcasting, right? So this is pretty simple. You provide two classes one above base class, one above here child class, or maybe below. Depends how you look at this. And when you actually use this in the code without those aliases, it looks a bit longer, but the pattern is the same. So how it works? This downcast base CRTP class takes the type as a template parameter, stores it in some internal public type, and what's really important here, it provides a declaration of a function called downcast guide, which gets at this argument of this type in this function, which basically allows us to call it as a friend function via ADL. However, at this point, right, we don't know what's the friendly user provided type here. We cannot know it because this is the one that basically is provided by the framework. So we are returning just auto. We cannot provide the specific type that will be recorded and will be provided for this translation of types. And we don't provide any definition for this function on this point. We just provided an ADL point, access point here, and the hidden friend function that can be called, but we don't know what's the result of it at this point. Then we have a downcastable concept that basically checks if our type has this downcast base type. And if it has it, it verifies if it's derived from downcast base of this type, right? So if we basically derived from this downcast base. And then we have downcast child. So this class that was injected between the child and the base class of our inheritance. It takes the target, so our child class, our dim speed in this case, and downcastable, so this long instantiation of dimension to be used as a base class for this hierarchy. And now we know exactly what's the target, so we can return this target. So this auto knows what's the type. But however, we couldn't provide this function only here, because first of all, framework will not see it because framework works only on the base class here. But also, this function cannot be called from this class because it uses the ADL of a base class ADL argument of the base class rather than the child class. So we are here providing the function that can be called, but we don't know what it should return. And here we cannot call this function, but we know what the return is, so we can provide implementation here. That's a really nice trick. It works. And thanks to this, I was able to provide the user experience. But before I will show you how it works in the code and what is the experience, first I have to describe you how the downcasting works, right? So right now we have downcast, again, an alias that basically is used by the framework. But now I provide the implementation for it. If it has downcast support, specific type provided by the user, I'm using this downcast guide with the argument provided to this downcasting facility, and through ADL, I'm finding this function and take this type from auto to know exactly what's the return type. If the downcast is not provided by the user, then we are just returning type T. And has downcast is implemented easily with required clauses. They just verify if downcast guide of argument is well formed. If it's well formed, then we are trying to get the result from it. Otherwise, we are just returning T. So the same as we had with the first case with the type thread. So how it affects the user experience here? This is the code written with my library right now. We have length, time, returning speed. We are dividing those, and we are doing the breakpoint. And the breakpoint in IDE looks as we expect. Finally, we see that there is dimension length, there is dimension time, there is kilometer and hour provided here as a unit. Also, breakpoint in GDB looks nice. Now we have average speed of a quantity of SI dim length in kilometers and SI dim time in hours. And of course, p-type also looks nice. This is the end of this chapter. So before we go further, I will see the question here. In the example debugging the concept function, how is debugging possible even before the program compiles? Is the compiler itself running under the GDP? No, actually those functions can be concepts. And of course, if you provide concept arguments to it, the compiler may choose to run it in compile time because it's not guaranteed unless the result of it is used in the compile time context too. So it's up to the compiler to decide if it's runtime or compile time, but basically you can only debug it when it's runtime, and most cases are runtime, right? If you don't provide many. Actually, most of the concept stuff probably are done in unit tests, for example, when you are unit testing stuff and providing fixed values to your calculations. But during runtime, you don't know units upfront. You may know some constants, but you are reading things like position, speed, and everything else from the GPS, for example, in my case. So in this case, you are just debugging this. With your last code example, if you cause a compilation error by multiplying rather than dividing, is the error message more user-friendly? Yes, it is. We'll come back to this later on when we'll talk about new toys in a toolbox, because I'm using concepts and I want to show you how concepts help here. Actually, I may not have the error log from concepts in the talk here, but yes, you will see information that basically speed concept is not satisfied because you provided wrong dimensions to it. I don't see any more questions, so let's continue. Okay, so everyone probably knows ratio, right? Ratio is a really simple type. Actually, it's a class template. It takes numerator and denominator and puts them as members inside the type. But actually, it's not that easy as it seems. For example, if you do something like 1 and 2 as numerator denominator, you have a half, right? If you provide 4 and 2, you have a half. If you provide 6 and 3, you have a half. So you have different types that mean exactly the same. And in order for it to work correctly, and in order for the library to know that all of those are exactly the same type, you have to do some more magic. And this magic is provided like this in most of the implementations right now. Basically, you're trying to find the greatest common divisor, do the division, and find out that all of them are actually 1 and 2. And then you provide another type here that just takes 1 and 2 here. So if you want to compare the types, you don't compare with is same on this ratio, you compare ratio : type if they are the same, because this one is already normalized. This one doesn't have to be. And this normalization, as you can see, takes a lot of class template instantiations in order to work. We have static sign, we have static ABS, we have static GCD to be implemented with class templates. Static sign instantiates integral constant, static ABS also, and uses static sign again with different value maybe. And static GCD is another instantiation of class templates. And those also use static ABS. So in order to calculate one ratio, see how many class templates you have to instantiate in the compiler. Then, if you have a ratio, you can make some operations of those, right? We can multiply, divide, add, and subtract ratios. Those, again, are class templates. Ratio multiply is actually an alias to the result calculated typically with a class template. Class template is implemented like this. And again, see, it instantiates those GCDs that basically instantiates a lot of other static, other classes, other instantiations. And then there's something called safe multiply that is one again a class template that basically checks if there is no overflow during compile time. A lot of stuff being done, a lot of instantiations to create such a simple type as ratio. With C++14, we got much better concepts, right? With concepts, we can make it better. We can reuse our runtime functions. We can use std.gcd, we can You can write ABS. Actually, ABS right now is not concept, so I had to type it by myself. But basically, this is what we can reuse. But most of the implementations right now in the standard library don't use it that way because it would not compile on C++11. And compiler vendors don't want to have that many branches in their implementations. So the implementations still use the class template instantiations rather than concept functions here. But there are a lot of, with this approach, there are a lot of less class template instantiations. Also, ratio multiply in this case gets easier because you can use again std here, make save multiply once again a concept function rather than a type the class template. So it should be faster. How faster we'll see in the last chapter. However, notice that this ratio is really tricky, right? We have this ratio, you have to use type instead of ratio to compare those because it's actually a value rather than a type. It's meant to be used as a value. And we use it as a type because we couldn't do this differently until C++20. So now C++20 comes, and C++20 extended a lot what we can do with non-type template parameters. Right now, non-type template parameters can be one of the following types. It can be either a structural type, or it can be a placeholder auto, or CTAT, class template argument deduction, placeholder. Structural types, so those types are scalars, L-value references, so things that we always had, and literal classes, which are interesting here because this is what's new. In order to compare two literal classes, we have to know when something is equivalent to one another, right? So there is a new term in the standard in C++20 called template argument equivalent. Two template instantiations are template argument equivalent. Basically, if they are template argument equivalent, they can be used and compare as non-type template parameters. And template argument equivalent values are integral types, so this is what we always had. Enumerations, again, what we always had. Null pointer t, floating point is new. We never had floating points in class templates or templates at all, right? Pointer type, pointer to member, reference, it was always there. But again, right now we have arrays, something new. Classes with template argument equivalent sub-objects and reference members. And unions. So see that we can actually right now use classes, unions, array, floating point numbers as template parameters. It provides us a lot more possibilities to work with our templates and provide better interfaces. So let's look at our ratio. Our ratio doesn't have to be a template at all. It's just a class, concept class. It has two members here. It has a constructor that does all of this GCD magic, right? When we want to multiply those, we just provide operator multiply here, rather than doing the ratio multiply class template and instantiations. And we reuse again those concept functions here. And what's even more interesting here, you don't have to multiply the ratios only. You can multiply value by ratio or ratio by value, which extends your interface to be much more developers friendly. So this is what we had to type previously with those examples. So this is what with studio ratio would be written, right? But with ratio as a class type, provided as non-type template parameter to a class template, it can be written this way. This is a constructor. This is division operator by scalar. I don't have to instantiate another ratio. And multiply operator. Also notice, this is also a non-type template parameter. We can provide strings, text, in order to instantiate the class template right now with C++20. It makes it much easier. Right now, I can define a unit for my library only with one class template definition, rather than rely on many macros that are common in pre-C++20 solutions to just create a lot of class templates and a lot of type traits, providing the symbols for the units and all of the needed information there. With this, I can provide all of the information needed in one class definition. And this is really, really nice. Before, when you wanted to compare two ratios, so for example, if you want to multiply ratio 2 by ratio 3/8, you had to do ratio multiply type trait, take the type of it, then verify is same with ratio 3/4, and again with type here, because you don't know how it's normalized by the framework. And now you can type something like this, right? It's way easier. And there are no class template instantiations here at all. However, those were really simple cases from unit tests. But how it affected my my design, my implementation, for example. I have something called base unit ratio. They basically calculates the ratio of all of the base units in a derived dimension. So we have a list of base units for length, time, mass, for example, and they want to calculate the ratio of all of them in the derived dimension. I had to write a ratio multiply and multiply basically the first element of the type list here, and multiply it by the result of the same type trait with the rest of arguments, right? So this is like a recursion on all of the parameters. We are taking one of the list and doing the same operation on the rest, and multiplying all of the results. Of course, we have to end this recursion at some point. So this is the end of this instantiations. When you have only one argument on the list, we are just providing this ratio type here. Otherwise, we are multiplying this and taking one element from the list at once. And right now, with ratio being a value, I can do for the expression to do it once in one function template. It's again much easier to maintain, much easier to write, and much faster to compile, because we are treating ratios as values. Sorry for this, I had some problem with camera. Camera, come back, okay. Okay, so I think that usage of class types as non-type parameters in templates might be one of the most significant C++ improvements in template metaprogramming for last decade. If you will take everything that behaves like a value and make it an NTTP, your code may be much easier to maintain, much easier to write, and also much faster to compile for the user. Do we have any questions? I don't see any questions. So let's continue to the rest of the toys. So now let's move to concepts. How do you feel about such an interface? We have function food that takes some void pointer and returns some void pointer. This is plain C, right? We are laughing from those interfaces, saying this is not a strong interface because we have strong types in the C++ language. We shouldn't write the code like this that takes everything and returns everything, right? We can do better in C++. But actually, do we do this? Do we do as we state? For example, did you ever written a lambda like this? Or maybe you written a function like this. Or even the C++20, actually, you can write it this way, because we have generic functions in the language. Or maybe class template instantiation or class template definition here. How it differs from this what we have in C, and we're saying this is a not strong interface, right? Of course, there is a difference, right? This C interface will fail during runtime rather than compile time. This one will always fail during compile time. But still, if you're going to things like cppreference.com or Doxygen documentation or any other reference guide for the library, you don't know what to expect. You don't know what to provide to this interface. It takes everything. It returns anything. And you don't know what to do with this function. That's why I claim that unconstrained template parameters are the void pointer of C++. And this is what we did for many, many years in the language. What are concepts? Class, function, variable, alias templates, and non-type template functions may be associated with a constraint in the language in C++20. Constraints specify the requirements on template arguments. So for example, you can select the most appropriate overload for a function to be called. A named set of such requirements is a concept. Concept is a named predicate. It executes at the compile time. And what's the most important in my case here is the part of the interface of your template, of your library. So the user knows what's expected to be provided there. During the discussion in Library Evolution Working Group, we defined 3 categories of concepts for current C++20. We have predicates, like derived from. Most of those concepts end with prepositions, like from, to, and so on. We have capabilities. These are single requirement concepts. In most cases, their names are like able, swappable, convertible, and so on. I have some. And yes, I'm sorry, I have some problems. Okay. And we have abstractions. We have high-level concepts, like bidirectional iterator, that basically provides a lot of requirements for the type to be successful. And those are generically nouns, like bidirectional iterator in this case. But are those all of the categories that we have in our language, in our use cases, in our libraries? And most of those come from basically range v3 and implementation of algorithms. And so this is what we learned so far. This is how we see the world right now, because this is what we did. This is what we explored so far. Do you know what this map presents? This is a medieval map of Sicily and how people perceive the world at this time. Maybe we need a different point of view of what we know so far. So if you look from this other angle, if you actually rotate this map upside down, you will probably start to realize some lens here, right? It starts to look familiar to us, just because we looked at it from a totally different angle. Let's look into our ratio multiply that we already discussed. This is how it's implemented, right? It takes 2 type names, everything, void star. So if I can provide everything, let's provide something. String, milli. Does it work? Of course it doesn't, right? But the user doesn't know about it. And we get a huge compile time error. So I would say that maybe there is one more concept category. I call it a family of instantiations, for example. And we have, for example, ratio as a concept. And we say this is satisfied by everything that's a ratio. And we can define ratio as, by default, this is false. And if it's actually instantiation of ratio, then it's true. And this is our ratio concept. And this category is named with an uppercase first letter of class template parameter that we want to match. Of course, it will not going to fly in the committee because we had this discussion already. But actually, this is the biggest problem I have right now, how to name this stuff. Because if you have a type called ratio, how to call a concept that basically matches all of the instantiations of ratio, or all of the types inherited from instantiations of ratio. If you have a good idea how to call this concept, please let me know, because there's a huge discussion about this on our physical units library issue on GitHub. Because we find it really useful, but basically all of good names are taken. For example, any ratio is taken rather by the polymorphic wrappers on types rather than the concepts. And it's hard to find a good concept for it, or concept name for it. But it doesn't mean that the concept is not useful here. In the one ranges proposal paper that merged the ranges to the standard, the authors said that the experience of the authors and implementers of the ranges TS is that getting concepts definition and algorithm constraints right is hard. The definition of those for ranges TS for all of the algorithms was really, really hard. And as you probably heard on some conferences, it's really hard later on to change it. We actually cannot change it in any direction, either make it more restrictive or less after it's standardized. That's why many people claim it and paraphrase this statement that defining concepts is hard. Let's try to keep their numbers small because it's something new. We don't have experience with it. And let's learn to use them correctly and make sure we are doing this right from the first time, because it's hard to change it later on. But again, this is what we explored so far because we have experience with ranges TS and range fill library. And maybe the world is bigger and different that we initially imagined, right? So for example, if you have a concept that basically matches any instantiation of a class template, like this one, is this concept easy to prove correct? Can you make error in this concept? It's just this, it's everything, right? It's correct by construction. So not every concept has to be hard. And we don't have to limit their numbers to just a few to make sure we are safe. Some concepts are really easy and are really helpful to make interfaces better. And if you have such stuff as a concept and you provide then something strange to ratio multiply, you'll get an information from the compiler that there are constraint failure because basically processes were not satisfied because its ratio returned false for the type provided, basic string long. Again, alias template rather than a strong type. Or maybe you want to say that something is ratio-like. So something that has numerator, denominator in the type, then it's a ratio. Again, is this concept easy to prove correct? It is. But again, it changes user experience a lot. If you again try to instantiate this class with those strange types, you get an information that basically there is no num and then members in basic string. Of course, we may say we don't want to have named concepts, right? Because maybe ratio is not a concept to be named. So we can use the requires clauses and just use type trace that we defined on previous slides. But basically it makes the interfaces much more verbose and much harder to maintain. This is a really simple case here, but if you're having a more complicated class template or function template, it's different. Having concepts helps here a lot, especially if you can use things like generic functions. And having concepts, as I said, is really handy here because we can define a lot of things as concepts. Let's look, for example, something like this. We want to implement a function, calculate fine for speeding. Right? We are returning price, and we take any speed in kilometers per hour, miles per hour, meter per second. We don't care. We just want this to be passing speed concept, satisfying speed concept. And speed concept is a quantity of dimension speed. Quantity of, first of all, has to be quantity. Dimension has to be dimension. So parameter d has to be dimension. And basically, dimension member in our quantity has to be the same as d provided to this concept. Then quantity may be an instantiation of a quantity class template. Dimension can be either a base dimension or a derived dimension. Derived dimension can be derived from instantiation of derived dimension base. And base dimension can be derived from base dimension. And actually, I cannot use the same type trait here because of some issues I will tell you later on. But I would really like to use it. So I had to create another manual class template here, just a type trait for this specific case. But concepts are not just a syntactic sugar. As I said, you can replace them with require clauses in many cases, and that just works, right? Or make maybe enable if, or make voice t usage somewhere. And you don't have to use concepts at all. However, how would you constrain easily a function return type with enable if, for example? How would you constrain a user variable that takes the result of this function to be speed with enable if or any other techniques? Of course, you can use decl type and static class assert here, right? But is that a solution here? Also, it's not easy to constrain class template parameters with enable if and spine, because it at least requires you to introduce additional template parameters to your class template and then provide class partial specializations of your class rather than implementing the primary definition of the template. One more thing about concepts that's really important, and what I find during providing C++ trainings to my students that people don't understand. What's the difference between those two columns here? We are creating a wrapper for type T. And we are having some data member of type T here, and we're having function foo that basically takes u as an argument. But we want to enable this only if type T is integral. Because, for example, modulo operation is not valid for floating point, right? And this is what people often do. Just do type names, enable if is integral T, and they think it's fine, but it isn't. It isn't because type T here is a fixed type already from class template. It's not a type provided to this function template, member function template here in the wrapper class template. So this T will not work correctly here. If you will check u here, you can perfectly fine work here, but T will not, because this is parameter of a class rather than this function template. In terms of concepts, it just works fine. It's easier to write, and it's error-proof. In order to make it correctly, with enable if, you have to do something like this. Saying, for example, we have parameter z that's by default a T, and then check the z. And you have to remember about it, but concepts and require clauses just work. With require clauses, you can even constrain a function that's not a template here. But again, with enable if, you have to make it a template and do this magic. So benefits of using C++ concepts. They clearly state the design intent, right? In the interface of the class or function template, when you go to cpreference.com or some documentation, you see exactly what the architect of this interface meant to be provided for this tool. Either class template or function template, or maybe template alias. They are embedded in the template signature, right? And they simplify and extend sphere tricks that we know. We can easily disable specific overloads, and it's much easier to do with enable if and error proof, as I've shown you on the previous slide. We can provide constraints based on the, for example, members of class parameters or validity of some operations. Much easier than with void t. Void t is great, but still it's pretty hard to implement. With concepts, it's much easier. And we don't have to do some tricks to, for example, constrain class templates. We don't have to provide any dummy parameters on the end of the parameter list in such class template just to make sphere works there. And as I said, we can constrain things like function return types or user variables, types of user variables on the stack, easily with concepts, which is just not easy to do with any other techniques we know right now. And they really nicely improve error messages, because instead of having a long error with many instantiations of the internals of the function template until some place when it stops to compile, all of the code is basically, all of the error log is provided for the top interface that you are running. You don't have to know the internals of the implementation of the function template to know if actually the error log is a bug in the library or maybe you provided a wrong type. Because all of the errors will be referring to the interface, will saying that constraint on the concepts failed. And you will never see insights or stack trace of insights of the library you are trying to execute or use. I see some questions here on the chat, so let's maybe answer them right now. For the ratio concept, would a concept which allows the numerator and denominator to be any integer type be more flexible? Yes, I thought about this, that we can provide such stuff, but we don't have such types right now. We had some discussion with numeric groups if we should make ratio dependent on some type, and for example, be able to provide really big integer types or other types as a denominator. But we decided to go other way finally, and ratio in my library actually doesn't have 2 arguments, it has 3. It takes numerator, denominator, and exponent, because this is how many SI units are defined. And this is how we make the scope larger for ratio rather than the one that's there, because the current ratio doesn't address even all of the SI prefixes, because 2 first and 2 last from the list are not supported by ratio because int 6040 is just too small. But yes, this is a valid case. We can think about making ratio a class template actually for this NTTP parameter and providing type T as its parameter, and then thinking about using some huge type that can express huge numbers. But we don't have those, right? At least in the standard. There are some in Boost probably and other libraries. And there's John McFarlane working on those for the standard library, but still we don't have those. Would using a different namespace for the concept be useful? Yes, we thought about this. We can use different namespace for concepts or have some _C postfix, like we have _T or V, for example, in the helpers. But on the same discussions in the library evolution working group, we said that we don't want to make concepts special. We don't want to put them in some specific naming conventions, like namespaces or _C or another postfixes. We want them to look exactly the same like types. So if you have ratio and ratio, I still don't know how to name them correctly. Maybe having ratio and concepts ratio or ratio _C would help here, But again, I expect it's not going to fly in the committee when I try to standardize this library later on. Okay, and that's all about concepts I have here. And let's move on. Let's see our world. Maybe it's even bigger or it's round, and then that we know exactly. So let's go to the wishful thinking chapter. So basically what we can change in the language, what limitations I found during my implementation. Templates are parameters by one or more template parameters, right? And those parameters can be either types, like smart pointer of int. They can be non-types, like 5 instut array, or can be generators, templates, right? Saying that I can provide any template here as a generator because my deleter here provided to this handle is not a type yet, because this my deleter is not instantiated with any type T parameter. It's just a generator to create deleters inside this handle. So knowing this, let's analyze such a concept called satisfies. We have satisfies, and we take a type trait. Yes, we have type parameter, template parameter here called trait, and we basically call trait with this type parameter to get this value. So for example, we can write our isRatio type trait here with false type, true type, and write something like ratio multiplies satisfies isRatio, satisfies isRatio, right? isRatio is a template, this one, class template, and this concept will check value inside and will either pass or fail. However, you've seen on my previous slide that I implemented ratio not this way, but using variable templates, and I will show you the benefits of it in the performance chapter. But you cannot provide isRatio to this satisfies. And actually, you cannot implement satisfies that will take this ratio, this type trait, or this variable type trait, or variable trait. Because basically, we don't have any syntax in the language to provide variable templates to a template. So template parameters work only with class templates. This is why I provided the P28 2008 paper, where I say that we should be able to provide both type names and basically non-types here. So variables, for example, variable templates to templates. It can be bool or it can be auto, taking anything that's convertible to bool, for example, in this case. Right? And I think those should compile fine. And in such case, we'll be able to use variable templates to work correctly with our code. If you have ideas for other cool solutions of this feature, because I know that many people already thought about it earlier, then please let me know. I will include your examples and your use cases in the paper for the motivation, because initial feedback from the evolution working group incubator is that they really like the solution and actually passed the paper to EWG, but say come back with more examples. So if you know more examples that can make this feature fly in the committee, please let me know and we'll include this in the paper. You'll be co-author of the proposal. We can play with it a bit, with especially when we have right now non-class template parameters provided in the language, extended in the language. There might be a lot of nice use cases for those. I have some ideas already, but if you have some also, please let me know and we'll work on those. Another extension is paper 1985. Imagine that actually we are not limited only to types, non-types, and templates, right? Because we can always provide one of those, but we cannot provide any of those. Imagine something that's above it, that takes everything. It's a placeholder that can be replaced with any of those kinds that we talked about. Our current syntax that is provided in the paper is called template auto. This class X says this is a class template. It takes everything. It can take value, type, or template. I don't care at this point. I just say this is a class template. Or I can say this is a class template with variable number of stuff. I don't care what's there, but this is a class template. And this is actually really powerful. For example, I can implement this instantiation of type trait that basically takes everything here and a class template, and if basically by default it's false, and if this instantiation is of this type with parameters provided, then it's true. And I can create a concept called instantiation of that basically uses this type trait. And with this, I can, for example, write easily instantiation of stud ratio. I don't have to type my is ratio anymore, because I can create one type trait that works for everything, not only for types, but also for non-types and for templates. I don't care what's the parameters of ratio. I just want to make sure it's one of the instantiations of it. And that's enough for me. And this feature will allow it. And again, compile time error, as you can see, always in the sources, never in the insights of the library, says that basically it's not an instantiation. Basic string is not an instantiation of ratio. Another use case for this is as follows. Imagine that we have factorial-like functions that create units. Coherent direct unit, named coherent direct unit, named scale direct unit, named deduce direct unit, named deduce direct unit, prefix direct unit, and take a lot of prefixes, a lot of parameters of void pointer, right? Of the same type. This is how C works, right? It's not strongly typed. That's why all of this has to be provided in the name. With C++, we can provide strong types to these functions. But actually, when you provide strong types, we used to create overload set. Because we don't care if the type is unit, we just want to create this unit. This is a factorial function. It has a bunch of overloads to create this function, right? I don't have to state every time and remember the name, long name, what are the parameters in this function. It's just to say, I want to create the derived unit with those parameters, and that's fine. However, if those factories are not functions, but class templates, we have to name them again with different names. And preconcepts, it's like void star. You can provide everything here, so you cannot easily determine what are the differences between those types. Right? Everything takes everything. Like void star on the previous example. However, with concepts, it's totally different. It's like strong types in the function interface. Right now, every list of parameters is different, is unique in this case. So again, instead of having those different names here, right now, I could implement this as saying derived unit is a class template that takes anything, and then provide a specialization for this, for this, for this, for this, for this, and for this, with the same name. And then if I want to create such a derived unit, I just provide template parameters for it and say derived unit, and I'm fine. And I don't care if there are types or non-type template parameters here, like string or ratio or whatever. It just works. So again, this feature turns to be really useful. Length. Right now it's implemented this way, units of length. Units of time is implemented this way. Units of speed are implemented this way. With this feature, all of them will just be derived unit with the list of parameters. I don't see any questions for this chapter, so let's continue to the performance section. We'll be talking about compile-time benchmarking with MetaBench. It was started by Louis Dion for his HANA library in 2016. It's a CMake module that simplifies compile-time micro benchmarking. You can benchmark not only all the translation unit to be compiled, but specific part of the translation unit you want to measure. You can find also on metaben.ch a comparison of many MPL libraries and algorithms out there. Okay, I see a question right now on concepts, so maybe I will answer this because before we go to the performance further. Do you think there is scope to extend concepts further by allowing the value itself to be constrained to a specific range or set, as is possible in ADA for safety critical systems? Of course, if you have non-type template parameter saying this is int, for example, or size t, you can constrain it. And actually, there was a nice talk about it on ACC Europe the year ago. And you can, and actually also have some use cases for this in my library. So you can also constrain non-type template parameters, saying that the value of size t has to be in the range from 0 to 5. It's totally doable with required clauses and concepts. And actually, it makes it much safer, saying that something is in the range of 0 to 8 or 0 to 3 or 0 to 10. And that makes it safer. Also, for example, in an embedded domain, just to have registers, and you know exactly what's the number of registers, and you can make register and non-type parameter in some class template. Okay, but coming back to performance. As I said, is a CMake module. So it has CMake-like interface, which we like or hate, depending on whoever you are, but still it works quite nice. You provide a target called, for example, stud ratio here, ratio type context, ratio NTTP. You provide the source file for this compilation, for this performance. It's actually a Ruby file. And you provide a data set to be used for measurements, and the name for this line on the chart. And if you define those three data sets, then you define a chart, saying this is a chart called creation of 2n ratios, smaller is better, and provide the data sets created above. This Ruby file looks as follows. Basically, you provide all of the definition here, and then you create a loop that basically takes n from this file in specific with specific data set, and makes that many instantiations of your code, in this case structures. That basically, if MetaBench is enabled, instantiates a ratio template, otherwise just creates a member type here. So if you run it, you will get test 1, test 2 with those data members and some ratios. For NTTP ratio, this is just this. And the results from running this tool is as follows. This is standard implementation of ratio with this class template instantiations. The orange one is the other technique with context functions being used that I said is C++14 compatible, but not C++11. So this is still not used in the libraries there, but you can find out that it's much faster. So maybe library implementers should provide such a branch in their library for C++14 upwards. But still with ratio NTTP, non-type template parameter, it's again faster because there are no class template instantiations at all. Everything happens in context. But as always with performance, you cannot assume that NTTP will be faster than the class template. Everything depends in C++, right? Always measure for your use case. For example, this is a creation of many ratios and some multiply and divide operations of those. So this is some black box testing of a longer calculation. However, when I divided this to specific operations being done, for example, to creations only, you can see that it was 42 seconds and creation took 2 seconds. So only a small chunk of it, but you will find that the creation of ratio NTTP actually was the slowest one because of this constructor run during compile time. I still make all of my calculations much faster because I gained some speed on other operations, but construction was the slowest one. And this was pointed out by Hanna Dusikowa on C++ Now, that concept is slow. For her use case on the compile time regular expression library, it took 2 minutes for DCC, 40 seconds of Clang, and less than 5 seconds for PHP. So our compilers are really poor interpreters of our code right now. We expect this to change. We expect compiler vendors to optimize on those, but still we are not there. Another interesting point on measuring compile time performance, I've learned on Code Dive conference at some point when Odin Holmes talked about Chill Doof, that was his intern, and right now they are working together on C++. Chill had a totally different approach to measuring performance of templates. He basically had a mathematical approach. He divided everything to the smaller pieces and started to trying to understand rather than just to measure. And the results of it was that the fastest operations are just looking up for a memorize type, because compilers memorize your class template instantiations. So if you run it for the second time, it's just looking for already something that was created rather than doing this from scratch. Second are parameters, new parameters to an alias code. Adding parameters to a type, calling an alias, instantiating a class, instantiating a function template, and Sphinx. Sphinx is the slowest thing you can do in C++ in terms of compile time operations on templates, because probably the slowest one is overload resolution, but this is a totally different story. So, for example, looking into the rule of Chill and how you can apply this. You know probably stud conditional, right? It's the type trait from C++11. It takes a Boolean condition saying which one of those types should be chosen, true or false. It's implemented typically in this way. You have conditional, Boolean, true, false as a primary template, and you say by default it's true. But we have also partial specialization on false, saying then choose false as a type. And then you have conditional T, that's just a helper provided to extract the type from it. With C++20, you don't need this type name here. With alias templates, you can implement this in a different way. Let's assume that conditional has only one parameter, template parameter, called bool. By default, it always returns false from this alias template inside this class template. And then, if you have conditional of true, then the type will always return true here. So you can see here you have template instantiations for every pair of parameters. For true and false, if they differ, you have a different class instantiation. Here you have only 2 class instantiations for true and false. The rest will be aliases in those class instantiations for different types. And as we've seen in the rule of Chill, aliases are faster than instantiating a class, right? So when you measure, you actually find the difference. This is typical stud conditional implementation. This is conditional with an alias. So when you are using this through this alias, conditional of T. But if you are hero enough, brave enough to use this long parameter, the long instantiation by yourself, then you can even save some time and be on the green bar here. Every operation takes time during compile time. On Clang, it's similar. What is missing in rule of chill from templates is variable template. Variable template is not there, right? Probably chill measured this before C++ 14. So let's see by ourselves what's the performance of variable templates. Let's implement the same in a traditional way. So class template, primary class template says it's a false type if the type is the same, true type, and the helper value helper here for is same, right? And you can do the same on variable templates, exactly the same logic. But right now we have variable templates here rather than here. And to get a type, we are using bool constant to get a type trait like a class. So this is inverse. The type is rather a helper here, or done using the helper, and the main implementation is done on variable templates. And now you can see on GCC 10 that stud is same v is the slowest one. Stud is same colon value is the blue one, and the is same value. So basically this, using this alias, so a type colon value is the same slow. But using the variable template directly, it's way faster on GCC. On Clang, there are some differences, but still variable template is the fastest thing to be possible here when you want to have different implementation specializations for different parameters. So as you can see, variable templates are really fast to compile. That's why I said that I would like them to be able to pass them as parameters to template parameters. So I would like to be able to pass variable template to a template. And it's not possible right now. And variable templates are the fastest thing to compile when you need the specializations, because otherwise use aliases. Those are the fastest ones. Talking about aliases, on CppCon, when I provided this example first time, it turned out that the talk on the same CppCon by other author also provided implementation of the same. So actually we had two talks treating the same. And the author provided such an implementation that it should be integral constant of bool with some wrapper is same. And here we are using the same approach that we are having only one parameter for a class template, and then we are using alias, not alias here. We're using overload resolution actually to find out which solution is better. And we are using the base class for the common case, so we don't have to instantiate it every time. However, it may be better from the memory point of view, and maybe on some compilers, but actually I measured this to compare with my implementation. This was disabled on my previous case. This is the last graph here. You can find out that this implementation, even though theoretically it's better, it turns out that the overload resolution process is really slow in the compiler, and this is this case on Clang. So it was the slowest implementation possible. So even you think that there are less class template instantiations, don't be fooled. Overload resolution is really slow. And this is Clang. You know what happens on GCC? I thought that the compiler hanged. You don't see even the graphs here from the other comparisons here. There is a logarithmic complexity here, exponential line, and basically the GCC refuses to work with you when you do such tricks without measuring first. So when you're trying new things, like this overload resolution process to make better, faster compilation time, measure. And this benchmark application, MetaBench, provided by Louis Dion, is great for it. And what about concepts? Let's analyze two simple stuff. We have two functions foo. We want to call one for them for m being even and m being odd. We can implement this with enable if and easily with require clauses. right? This one will be called in this case, this will be called in the rest of the cases. Similar as here. And actually, I also checked the if context implementation. It's not an overload resolution anymore, but still is a valid way to do a tag dispatch or dispatch during compile time. So I also compared if context with the implementation. And here's the graph. Sphere is the slowest one. And you can see that if context and concept are having the same performance. And we are saying that if context is fast, right? From C++17. So adding concept is the same slow or the same fast, depending how you look at it. So if you want to make a dispatch, having the concept or having the if context is the same fast. Of course, in some cases, this may be preferred solution. In some cases, this may be preferred solution. But please don't be afraid of concepts and their performance. And still, this is really first implementations of concepts. Maybe they will be even improved in the future, right? In terms of the quality of implementation in the compilers. In Clang, is similar. So this is similar to different compilers, not only to those two. From my experience, if you are afraid of concepts performance hit on your library, you can save those at some point. I don't say that type name is always wrong. Don't use type names if you have some constraints, some assumptions about the type in the user interface, right? So if you provide a dimension with exponents, and the required exponent to be provided here, make it an exponent so the user knows exactly what is provided here. The same if you make a dimension divide, like ratio divide, say those have to be dimensions. But later on, when you already instantiated a dimension with exponents, you don't have to type exponents here because you already validated this when this type was created. You don't have to validate it again, right? Because it was already, otherwise this type would not be constructed if this fails. So you don't have to check the concepts again here. Maybe because of memoization, if the compiler will implement memoization, and some of them already do, it will not take any time because memoization, as you've seen, is really, really fast. But I don't know. So in some cases where there's not an external interface but my implementation details, I skip type names because here I know that this dimension is already satisfied by this concept. And here, this is my internal details, so user will not provide bad types because those types were already checked here and then provided to this implementation here. So if you, oh, I see that my camera froze again. Sorry for this. I have some problem with my set. And yes, so if you measure this, again, if you measure this, this is concepts everywhere. This is no concepts at all, just void star everywhere, type name everywhere. And the orange bar is when I'm using concepts only where needed. There is some hit, but you can see this is like 10 to 20% of the compilation time. And this is not done for nothing, right? You pay for what you are using. So basically, this is you have to pay for something if you want to use concepts. But as you can see, totally, it is not that much slower. And as I said, it's as fast as if concepts, which we claim to be fast. If you're interested in metaprogramming tricks, in the performance and benchmarking of those, go to MetaBench website and see how different libraries perform with different algorithms, like sort, for example. You'll find out which is the fastest one. You can go to the implementation, see how it was implemented, and learn from it to write faster template metaprogramming code. Takeaways, because we are nearly out of time or out of time already. Sorry. Rethinking C++ templates. First, think about end user experience and not only about your convenience as a developer, right? Template aliases are great for you, but are not great for users. If you can provide better user experience, provide it to your users. And maybe we should start again voting for strong type defs in the language. Let's write a new, better proposal. But I think that Walter did a really good job there, and it will be hard to convince the committee to accept it. Use C++ concepts to express your compile time contracts. Improve the productivity to improve the error logs provided by your compiler. Use non-type parameters every time your parameter of a template is value-like. If it has value semantics, if it behaves like a value, probably it should be an NTTP. And optimize compile time performance. Metaprogramming tricks are free at runtime, right? We are doing everything in compile time, but it doesn't mean that during compile time everything is as fast or as slow. There are different techniques, more than one way to do it. Choose the fastest one, measure, and be smart there. And as I said, always measure, because even if you think that you know everything, even if I think that I know everything, I can be wrong. And people say speaking at CppCon can be wrong. Everyone can be wrong if they don't measure. Always measure to make sure that you are right. And that's all from me. Thank you very much for joining this talk. We had some questions during the talk. I don't see any more questions right now. So probably we will finish the stream right now, and you can find me in the lobby to take more questions. Thank you, and have a good time.